Okay, as people are coming in, I already say a hello and good afternoon, good morning. And thanks a lot for your time, for joining us today to the Code for Earth 2026 Coding Phase Midterm Webinar. And I'm here with my colleague Esperanza Cuatero. We are both
Hello.
the coordinating team for Code for Earth, and we are supported by our colleagues from Compla Trust IT, and today it's Sara Bozzi, but usually we have also Diego Domenici. So good. And as people are coming in, let me give a short intro to Code for Earth very briefly before we dive into the projects, respectively, what the projects team have been doing so far. Quick facts about Code for Earth. Code for Earth is a key innovation action that is run since 2018 by ECMWF, by the European Center for Medium Range Weather Forecasts. And the program is supported by Copernicus, the Atmosphere Monitoring Service, and the Climate Change Service. Destination Earth and the European Commission's ArcX Global Gateway Program. That's the Africa Regional Centers of Excellence program of the European Commission. So the program is addressing mentor-identified challenges, in the broader domain of generally Earth science, but specifically, of course, looking into weather, climate, and atmosphere. So each summer, we have a group of teams, individuals or developer teams from different backgrounds, be it in earth science, AI/ML, data science, computer science, on software development, and they all work on these mentor-identified challenges. It's all about innovation, collaboration, and open source software development. And those teams, those of the selected teams that successfully complete the project, they will get some financial contribution. Very short timeline, where we come from. So we had the call for participation earlier this year. Some of you might have participated and submitted a proposal. Then we had a selection phase in April, and now we are at the coding phase. And talking about the coding phase and the challenges, I would like to say a big, big, big thank you to our supporters this year. So we have ENSO-E, the European Network of Transmission System Operators. They are second-time supporters. We have the University of Reading, who is supporting a project. And then under the Global Gateway Program, we have ICPAC, the IGAT Climate Prediction and Application Center, and last but not least, AfriClimate AI. That's a nonprofit research organization that is working on and with AI for sustainable and climate resilient Africa. Thanks again for supporting and being part of this year's journey. Talking about thanks, I would like to hand over to my colleague Esperanza.
Thanks, and a special thanks to all the mentors who are supporting the teams in this edition. We have a number of 53, and they are guiding our teams along this journey from conference. And these mentors come from ECMWF, but also coming from the partnership organization that has just mentioned. A big thank you to all of you. And today we are very, very pleased to welcome and to present 7 projects out of 14 which went through the coding phase. These projects are Power Climate Vision, Atlantis, AtmoLens, Weather to Grid, MAST, Coastal CEI, and Tree Hydrate. So without any delay, let's hear from the teams. They are the real main characters here. So please, we start with the first one, which is the project is Power Climate Vision, and the teams, the person behind are Alessandro and Vlad. I think they are the presenters. You are sharing your screen. The floor is yours.
Just for some logistics, please, to the participants, if you have any questions, please post them on the chat, and then we will come back to the questions at the end of the session.
Yes, when the last presenter. Yes. Alessandro, yours.
Yes. Could you see my screen now?
Yes.
In presentation mode?
Yeah.
Perfect. So my name is Alessandro Dumitrescu, and together with my colleague Vlada Mihaise from National Meteorological Administration of Romania in the Department of Climatology, we're selected to implement this Challenge 14 from the Stream 1 data visualization. In one sentence, what we are supposed to do, we are supposed to make the pan-European climate data set information presented in an easy way to be visualized and explored by European power sector. Yes, as mentors, we of course we have ECM scientists from ECMWF, but also we have from mentors researchers from European organization which activate in energy sectors, and they plan a reliable European electricity system. For this, in this way, it is very important to know how the climate change will affect the renewable energy in a different climate scenario. So pan-European climate data set offer valuable information for this. So it contains a lot of data from 1950 to the end of the centuries for the historical period, as well for different models and different SSP pathways. So we try now to make this information explorable for power system planning. We built our application having in mind that a power planner could access the information based on three important things. So a power planner first must select which country, region, or power system zones, which are defined already in the PACD dataset, which climate indicator wants to analyze, and of course under which climate scenario. So in our power climate visions, we put all of this in one map, one regional trend, and in an exportable data sets. Now I'll give you some screenshot from our applications. Use the one second, please. Okay. So we have here in the left side part of the screen the controllers, meaning the filters from which the user could select the region of interest, the climate or power indicator, and of course the scenario and different period and the period from for which the data is average. Here you could see by clicking on polygon, this kind of graph is generated, and power planner easily could see how the historical period and future time horizon for climate scenario looks like for a given indicator. In our case, wind power capacity factor. So the data could be, we implemented a lot of options here in which the data could be visualized. So the user could use a time series plot with the models agreement, or could select this option multi-scenario time series, in which the planner could see how the different scenario, until when different scenario agree, and how the disagreement looks like for the overall time period. So we have also annual cycle and multi-scenario annual cycle as Boxplot implemented there. There are a lot of information could be visualized, and of course could be exported, like I already mentioned, in the CSV file all the information which is behind the visualization part. So this is the workflow which we have used to implement our application. We started from Pan-European Climate Dataset PSD version 4.2. We process a lot of data. It contains historical data and projection, like I already mentioned, at hourly and daily scales. We linked the time series with the spatial tiers, which they are already defined in the data sets, and we integrated all of this in an interactive environment where the user could see the information as map or as regional trends, and could perform climate scenario comparison, or could export the data in a tabular format. This is what we did so far. We have already in place a tool which could be used to visualize the Pan-European Climate Dataset, offer various ways in which the information could be accessed and visualized. User could have a look only at the historical data or at the project ensemble medians, or also could have a look at the model uncertainty. The data could be exported in a CSV format. As next step, what we like to do to implement the indicator which remain to be implemented, like hydrological power, to validate our workflow with the workflow with our mentors, to complete the documentation, the maintenance guide. And we also like to refine a bit the application if we have time, and if we receive some feedback from the users. Here in this QR code, you could access the actual version of the visualization app. And if you have some comments or some suggestion, please don't hesitate and let us know how can be improved. So this was in brief about our work so far. If there are
many things, Alessandro, are very promising. Your projects. Thanks for presenting. If, as Athena says, if someone of the audience has a question, we can allocate it at the end. There are a ton of questions and answers at the end. Thank you very much. So now we the spotlight is the project Atlantis. Yes, it is Stylianos and Ioannis are the brain behind this project Atlantis. The floor is yours when you are ready. Yes, you already saw the screen. Go ahead.
Okay,
thank you.
Great. Hi, everyone. I'm Yannis Kalfas, and together with my colleague Stelios Lagaras, we built Atlantis. So Atlantis is a scalable multi-source flood observation archive for ML. What this means is that we're trying to transform all the scattered or fragmented Earth observation data that relates to floods into a unified archive that can be ingested by machine learning models for flood prediction. So, as you know, floods rank among the deadliest and costliest natural disasters. They cause a lot of damage every year. And we're trying to predict floods. We need to have some very well structured and high quality data so that we can feed them to machine learning models. But in reality, the flood data is scattered across multiple sensors. It has different resolutions, semantics, coordinate systems, and so on. So what is happening is that machine learning teams spend a lot of time trying to organize this data instead of building the actual models. And this is what we're trying to solve with Atlantis. So what Atlantis does is to ingest raw flood data from various sources. So far, we have VIRS, MODIS, and GFM. And we also introduce pluggable fetcher registry, which means that we can very easily ingest additional sources in the future. Then we harmonize this data into a canonical one ArcMin global grid of 1.8 kilometer resolution, which is commonly used for modeling tasks in ECMWF as well. Then we compute some derived layers, as we call them, which is the water fraction, reference water, for example, where you have water and how much, if it's permanent water or not. and also some exclusion masks that show invalid pixel observations. And in the end, what we output is the machine learning archive, of course, and we do that in two formats, both GeoTIFF and ZAR v3, that my colleague Staios is also going to talk about soon. So the architecture at a glance, the most important base class we have is the flood event base class that is defined by an area of interest, or the B-box as I show here, date range, and the sources. So from which satellites you want to read data from. We built fetchers that basically they are software parts that deal with fetching the data from online locations, for example, a cloud bucket. You see already that they are different resolutions, and that's one of the problems we try to solve. Then we have harmonizers, and here is where we do the reprojection, normalization, and tiling to bring the data in a shape or format that we can easily work with in Atlantis. And these two components are already fully operational. What is still work in progress is the archive writer, where we will save the data in GeoTIFF and ZAR, and the stack layer on top that my colleague will share soon. On the right, you can also see the command line interface we expose. It's very intuitive. You just need to define an event name, the sources, so from which satellites you want to read, the area of interest, start and end date, whether you want to harmonize the data, or maybe you want to fetch the raw data, and whether you want to read some plots. Now, we're dealing with a lot of data across multiple dates, so we have a single strategy for dealing with that. For example, if you give a large range, you can select to return only the peak flood from that. So basically the scene where you have the most flooded pixels. You can also have the aggregate strategy where you return a temporal composite, where you apply layer-specific operators depending on whether your data is categorical or float values, for example. And then the strategy for all returns all the observations that you have available. Now, on top of that, we have a windowing function where you can select a range of ±2 days, for example, as I show here in the image. And then you can select to subsample those and say, for example, I only want maximum 3 observations from that window. And of course, you can combine that with the all and aggregate strategies. Now, the key innovation of Atlantis is, of course, bringing all these sources that you have incompatible encodings, different resolutions or semantics, and creating these harmonized derived layers. So basically the water fraction, the reference layer, and the exclusion mask. And from then on, you can perform the analysis or modeling in a much easier way. On top of that, of course, we expose the intuitive CLI and then the data formats that my colleague will explain. So at this stage, I will pass the word to Stelios to continue with the scalability test.
Hi, everyone. I'm very excited and happy to be here with you today. So I'll speak a bit about the operational parts of Atlantis. We have established a pipeline to process a catalog for VIRS for 2020. We have done this in our local virtual machines, processing around 50K of products in half a day in a virtual machine. And we store the output in an S3 storage in an optimal way, in cloud optimal GeoTIFFs. And of course, an important element is that we have established a recovery mechanism. So if our processing at some moment breaks down, we can recover from the last checkpoint we stopped. We can go to the next slide. Now I'll talk a bit about ZAR. ZAR comes as the cherry on the top of Atlantis. It's the next generation of our pipeline. We use ZAR primarily as a endpoint of requesting the data. So instead of the typical way requesting a raster file, now we're requesting an area of interest and a time context that we are interested to examine. We developed the pipeline also producing the output in ZAR in optimal chunks for the next step that it's going to be the ML digestion of this archive. And we have run this processing for 2024 for another complete year for VIRS, which we can go to the demo all together into the next slide. So here you see lively how our local server is requesting the data for the event of the Valencia flooding. Yes, we can see it one more, and the event expands, and as expected, at the end of our time context, it diminishes. And we do all this, but we don't compromise. We want to really give to our researchers a relief of the technical burden. We want to take over from their shoulders all the backbone and the details, the tooling. So we have put a lot of effort to keep our code base and our tooling as zero configurable possible, and with a nice also visual result, as you can see on the right slide. And at the end, we can speak about the goals, the future goals of Atlantis. So we want to complete this back archive processing for multiple platforms that we accommodate. And then we want to pass this to the NRT mode. So to establish a near real-time operational pipeline that is triggered whenever a new event is published from these providers. We aspire to continue the project as we enjoyed very much, and hopefully it will find some real cases and applications. Thank you very much, and we hope to see you all in Reading in September.
Thank you very much, both. We are looking forward to see all of you in Reading.
Esperanza, maybe I can just, I'm not sure if I mentioned it clearly at the beginning. So for the audience, we are kind of halfway through the coding phase. So we see now we have a spotlight on where the project and the project teams are. So, please ask questions about, what are the next steps or what are ideas. Don't be shy. But don't expect that everything is clear yet, because the teams are still working on the programs.
Yes, exactly. And they half coding phase to finish it. So there is still plenty of time. And now we have Atmolens, project Atmolens. Devjit is with us. So we are looking forward to hearing from you, your intro, the project, and yourself. Yes, we
Can you hear me?
Yes, we see your screen, but if you put in the presentation mode, will be perfect. Yes.
Okay. So good afternoon, everyone. So this is Project Atmolens. The goal of this project is to come up with an automated end-to-end Python pipeline for detecting and characterizing air quality events. That has been happening all over the globe. So yeah. So just to discuss the problem that is there right now, what ECMWF uses is a system which is based on fixed field values that you are generating, which is the raw AOD value. AOD is aerosol optical depth, which is the unit in which you calculate how much amount of dust is there in the atmosphere. Or so dust is one of the variables. You can have many more variables. Here, the case study that I have taken is based on dust, aerosol optical depth. So right now, what ECMWF uses is fixed values of this field. Without any comparison. So in the sense, when I talk about comparison, if you talk about Sahara and if you talk about a place in Scotland, you cannot have fixed value for a value or a threshold fixed based on the standard AOD values itself. So for that case, you actually have to come up with another form of standardization that I'm going to discuss later. So this is one of the problems with arbitrary cutoffs that is there in the current ECMWF systems. Secondly, there is no structural information of the events that are there. So, for example, if you have a plume of dust, you actually don't know how much area it is covering or in which direction it is moving, or I mean, the characteristics of these kind of plumes. Yeah. Then thirdly is like non-stationary background, as in like there is no characteristic threshold fixing for seasonality or changes like annual changes in time. And lastly, poor transferability. So when I talk about poor transferability, ideally any pipeline you should be able to transfer it to different variables altogether. So right now the transferability is also poor when I talk about the current system of ECMWF. Yeah. So yeah, the goal is to come up with an automated end-to-end pipeline covering all this aspect and statistically driven. Yeah, so just talking about the background, how it works is basically, so there is a Dask compute engine which kind of ingests data uh, from the CAMS reanalysis as well as the CAMS forecast, because reanalysis is something that we need to calculate the mean and the standard deviation of any field that we are going to use. And also for the forecast is the forecast data that ECMWF is generating every day. So the idea is for this pipeline to work on that particular forecast data to characterize events in that particular forecast. And then there is a pipeline which I've developed, which works on like 3 different pathways and to come up with an ensemble approach at the end. So there is branch A, which is more on adaptive thresholding. Branch B is more on Hessian ridge. I'm going to explain them in details in the upcoming slide. And lastly, there is structured and visual outputs. So basically, you will be seeing what kind of events that are detected in terms of visualization and plots at the end. Yeah. So when I talk about the first part of the pipeline, it is mainly calculate, as I told you initially, like right now, ECMWF uses the standard field itself without even standardizing it in terms of mean and the standard deviation. So that will exactly harm the cause when it comes to comparison between Sahara and Scotland, because the dust conditions, the atmospheric compositions are totally different. So you cannot rely on the raw value. So that is why standardizing this field is the most important thing in terms of mean and the standard deviation. And you can actually see on the left hand side is the exact value that is there in ECMWF's raw field, and the right hand side is the standardized field that I'm creating out of this in the image. Now moving to the first branch of the detection pipeline that we have created. So what it does is that it works on adaptive thresholding. Now, when I say adaptive thresholding, what it does is that when you see the middle image, you have the standardized Z-score, right? Now, the first step is to get rid of all the values that are not in the top 5%. So once you have that, you actually divide it into so how you do it is you create a binary map out of that. So all the region that is in the 95% band will be marked as 1, and the others are marked as 0. And then eventually you create blobs of these ones that are there in the map. So what you will have is small regions, as you see in the last image, which is in the extreme right. And these are basically the plumes that you would be seeing in a forecast, or the idea was to detect these plumes actually. And the centroids of those plumes. Ideally, I have a lot of information regarding each of these structures, which I have not shown here, of course, but yeah. So that is the characterization of these plumes. Then moving to the branch B, this is one more layer of detection wherein it focuses on the Hessian ridge. So basically, what it does is that it uses the Hessian matrix to calculate the change in slope of these plumes, and ideally calculates the spine of these plumes, which you can see in the fourth image, the blue one, which calculates the spine of those plumes. And the green one in the last image is actually the current forecasting system of ECMWF. So yeah, so our goal is to see how better we can do when we standardize this field and come up with these kind of detection and implement these kind of detections. So after this backend, I would like to focus on the front end or the UI that I have developed. So it is a React 18 based UI with Docker containerization and Nginx ingress. And later on, the idea is to host this UI for people to use. So this is the interface of the UI where you can see all the plots and the fields, and these plots are actually interactive. So you can just zoom in, you can see values of each events here. And also, you can open the panel on the left-hand side to select the dates and also the forecast lead times. So basically the time steps of the forecast. There are 120 time steps, which ECMWF currently generates, which is the 5-day forecast. So yeah, and also at the bottom, you see all the events and their corresponding characteristics. So all the events, their centroids, their area, how much each event is covering. Yeah. And also you can see each branch as well if you want to see what each branch is detecting. Yeah, so that's it for the current developments, and the upcoming tasks will be to do a time series of these each individual events to see how much they are moving in time in those 5 days. And we can track and detect a life cycle out of it, make a life cycle map out of it. And lastly, the aim would be to move to 3D atmospheric fields, because currently all the developments that you saw are on 2D fields. So we will be moving towards 3D fields as well, so that we get more better results. Yeah, that's all from my end. Thank you.
Thank you very much, Terkit. Very much promising. You are very nice. You great that you still have time to do the final touch. Very nice. Mark has sharing in the screen examples of the aerosol optical depth plumes monitored by cams that AtmoLens will be used. So if someone is interested, please click there. And now we have the next project, which is Weather to Grid. It is formed by 4 members, which are in the same room, I believe. They are Quentin, Emma, Nora, and Visnupriya. So the floor is yours. When you are ready, please share your screen.
Hi.
Yes, perfect.
Hi, everyone. Thank you for having us. We are Vishnu, Quentin, Nora, and Emma. Our project is Weather to Grid. And in this project, we explore how we can use machine learning methods and large-scale weather patterns to improve subseasonal energy forecasting. So to motivate this, we can imagine a simple situation. So imagine if you are managing the energy market of Europe for the next 2 to 3 weeks, then you will need to know both sides of the market. You will need to know how much energy people will demand and how much solar and wind power production will be there to meet this demand. So these variables are closely linked to the daily surface weather conditions. The surface temperature influences the energy demand. The wind conditions influences wind power production. The cloud cover and solar radiation influences the solar power production. So essentially, you will need to know the surface weather forecast for the coming weeks. However, the surface weather conditions can be hard to predict in longer lead times. So instead of directly looking at surface weather conditions, previous studies have looked at upper level circulations, such as geopotential height, and identified weather regimes or large-scale circulation patterns. These weather regimes are more predictable at longer lead times and are closely related to surface weather conditions. So technically, knowing these weather regimes, you can know the variations in energy demand and production. So this sounds very promising for energy forecasting. However, there is a challenge.
So here in this slide, you see illustrated 4 of the main classical weather regimes for the North Atlantic. So wherever you see blue, that means rather low pressure system conditions, and then red is associated with anticyclones. And the thing is that when you try to look at the mean solar power production in each of these regimes, then you'll see that there is some informativeness. That is, for example, in the second regime that you see, there tends to be less than usual solar power production over the Iberian Peninsula, just because there's more storminess in that region. But the signal is relatively small. It's about a 5% reduction compared to the mean. And in some of the regimes, you actually don't get any information as to the solar power production. You can just say, well, it's as much production as the average. So while these regimes are interesting in terms of predictability, they're not necessarily very informative of the variables that we are interested in, that is energy demand, energy production. Next slide.
Can use the mouse.
Perfect. Oops. All right. So the method that we leverage here comes from a recent study by one of our mentors, Fiona Spuller, and essentially uses a machine learning technique to find alternative regimes than the traditional ones that are being employed, that are hopefully as predictable, but that are also more informative of the target variable. And so for those who might know a little bit about machine learning, the way that this works is that we use an architecture called an autoencoder, Well, the general point is to try to start from a given input map of the mid-tropospheric weather and to put it through a neural network that compresses it into a very low dimensional space, then tries to reconstruct it. So the hope is that this one vector here will retain all the information about the large-scale weather, but will be just a compressed representation. The thing is that then with this compressed representation, you can do things like cluster it to find regimes. But the way that this is actually done here is that we actually define the regimes directly in this low dimensional space. So rather than predict a compressed representation, we try to directly predict the regime number that is then used that is then associated with different parts of this low dimensional space. So for now, I haven't talked about the target variable at all. What we try to do, and that's very simplified here, but in essence, what happens is that we try to shape this low dimensional space so that different regions or different hills in this in the distribution of this low dimensional space correspond to different target variable conditions. That is, for example, for solar power, we try to do so that one set of the low dimensional space represents more solar power production in the south of Europe and less in the north, etc., etc.
Okay, so now let's have a look at how this looks like if we apply it to wind power production, for example. So what we did here is that our target clusters, which is what kind of helps us to shape this this latent space, are these 4 clusters, predefined clusters of wind energy production. And as you can see, the different clusters represent having more or less energy production in different regions of Europe. So for example, cluster 0 has high wind energy production in Central Europe. And now if we use this as a target variable and train our model, then these are the best regimes that we found. So what you see here in color is the geopotential anomaly of the 4 regimes that we found. And basically the red means that we have higher pressure than usual, and the blue means that we have lower pressure than usual. And from this we can kind of deduce the large scale flow. So for example, in this case here, the large scale flow will be relatively strong westerly flow. And this actually corresponds quite well to cluster 0, because in this case, we also expect to have high wind power production in cluster 0. And this kind of works also for the other regimes. So visually, it seems that our large scale flow regimes correspond well to the target clusters that we had. But now we want to assess this a bit more systematically. And that's why we looked at the Brier skill score. And here the idea is that the Brier skill score should tell us how well our regimes that we found predict different categories of wind power generation. So for example, here in this first column, we show how well our regimes predict the target clusters themselves. So this is really what our model was trained to do. And you can see in black, this box plot shows you different training runs and what their scores were, like how well the regimes performed. And in orange, you can see how well classical regimes performed, which were computed with PCA, principal component analysis. And you can see that at least most of our runs, regimes that we found, were performing better than the classical regimes. And then in the second column, you can also see how well our regimes predict days of very low wind power production and for individual countries. And we can see that the skill score drops quite a lot, but at least we're still performing a bit better than the classical regimes.
Yep. We also evaluated the predictability of the circulation regimes identified by classical PCA and the CMMVAE method. So we can see that the CMMVAE performs pretty much similar to the PCA. So it shows that the energy targeted regimes does not lose predictability. Okay, Emma?
Thank you.
And,
so we presented the context and the result that we got until now. And the idea of the project is really make that available to researchers to try on their own data and have such regime for different target variables. So that's why what we're trying to build is this package, which should be easily installed by anyone. And that would allow anyone to train a model on their own data and then to run inference and to evaluate their model. So that's the structure of our package. We would have our package, the name we didn't define yet, but a first package that would allow to do pretty much everything we showed on any data. And then we also provide some examples that we just presented with result and like Jupyter Notebook to be able to do that in another setting. So yeah, that's pretty much the structure of the package. Thanks. So what are we left with now? So we built most of the package except 2 modules. The first one is the fine-tuning. So the idea is to allow users to have more flexibility to do some grid search or cross-validation to have better models or the best model they can. And on our end, that would be to apply this fine-tuning to our data, so energy data and model. We also want to work a bit on the data processing. So right now it works well on the data, but it's a bit of work to make it work on any data. So we'd like to build a module to make it easier for the user to apply to their own data. We also want to do like some kind of interactive platform or website to demo our model and the performances on real-time data. So that's what we have to build. And finally, I guess we need to write a bit more documentation, even if the code is right now fully documented, and if we have enough time to improve the performances of our model.
Very good. Thank you very much, team. Well, that's great. Very impressive. So,
yes. Thanks a lot. And sorry, Esperanza, to chime in. Yeah, we had now 4 of the 7 presentations for today. And so if you're wondering, oh, what will happen, once the teams are done, wait, there will be a final day in September, and we will announce this also publicly. And it will be a hybrid event, so people can participate online to the event. So this is only just a spotlight about now. Where are the teams now? And in September, we will see the projects, how they finally look like. So Esperanza, I hand back to you. Sorry.
It's fine. And now it's time for MAST team. This is one of the projects of a new Africa stream. So this MAST team is formed by 7 team members. Oh no, sorry, 8. And I don't know who is going to present. The floor is yours, Lester or Mark.
Just a moment. First, something. So just a moment. Need to hide this one. So
yes, we can see your presentation now.
So can you see it on?
Yes, we can see in the presentation mode. Yes, you can start when you are ready.
Okay. Thank you so much to ECMWF and the Code for Earth team. So basically, our project looks at monitoring and understanding spatial-temporal flood risk toolkit, majorly focusing on East Africa region. So I'll be assisted by Mr. Mark in terms of the presentation. So the challenge we're trying to address is the challenge dubbed number 41 that looks at missed opportunities in flood risk management. So basically, setting the context in terms of the flood events in Eastern Africa, they have been increasing in frequency and intensity over the past few years. With the last flood of 2026, March it recorded led to a death toll of 66 deaths in Kenya. So, but then we do have data within ECMWF, Cloud, and Sembo Forecast, which are then in terms of petabyte, which are currently under not cloud native, not systematically evaluated, are not linked to impactful decision making for the Eastern Africa region. So, but then our challenge now looks on the backdrop of this to transform the complex ECMWF probabilistic forecast into timely, interpretable, and actionable insights that directly support decision-making in disaster management agencies, meteorological services, and the local governments. So depending on this, we employ a three-layered approach on how we want to bring the solution. So first of all, now we make the ECMWF cloud data into a analysis-ready format. And then from there, we are able to compute some exceedance analysis on the return periods for the flood. Then from there, we target now to have a visualization dashboard that then the users in the disaster management agencies and meteorological services can be able to make informed decisions. So at the end of it all, now we want to ensure that the forecast that's available from ECMWF is linked to real-world decision-making, which will enable to strengthen anticipatory action, save livelihoods, and protect lives. So in terms of the data structure, here our source of data is the ECMWF within the cloud, S3, and then our grid index files are stored within Hugging Face. And then we calculate our rainfall return periods based on the CMOP data. And then after that, we are able now to transform after having the rainfall return periods, and then we do have the ensemble forecast from ECMWF. So are we then now able to transform into actionable decision making by having a visualization of the events where certain thresholds were exceeded in terms of a calendar display, and then from that, then linking with the EMDAT database, which contains the impact data. So from there, we can link now and have like, well, this event exceeded certain threshold, but then which impact did it cause in terms of the lives, in terms of the people affected, and what are the in terms of decision making, what steps should be taken. So in terms of, we've developed a dashboard, so maybe I can welcome Mark on board to give a short overview of the dashboard that we've developed based on the various datasets that we've fetched from ECMWF.
Thanks a lot, Lester. So in terms of the system, we have two main pages. You have the events page, which is the first page that you can see. And then we have the story map page, which is basically the rest of the three pages. You basically scroll down the story. So in the first page, you have an GitHub style calendar. I hope you can see it. Maybe it's inside here. Yeah, the GitHub style calendar. In that calendar, you are able to select each cell is a forecast day. And you are also able to select the accumulation and the return period and the year. You have some selectors just above the calendar. And you also have an admin one risk layer, whereby you are able to visualize the admin one areas that are at exceedance risk. So how it works, we already have.
Sorry to interrupt. So are you live demo, or do we see the slide that Lester has shared?
Yeah, so this is just the slide.
Okay, good.
Yeah, this is not the live demo, it's the slide.
Okay, yeah.
So you select the date, and then the color of the choropleth map on your right hand side will light up in either yellow, amber, or red, depending on the severity of the exceedance probability. So each admin one level is going to show some sort of signal. And so once you select there's some statistics that comes down here. You have the date, the severity level, and you also have the return period, and you have an icon that can lead you to the story map. So once you click this blue story map, you come to the next page. This page has a widget on this side with some background. This widget tells the story. This map visualizes the conditions. So on the first widget, you have the signal. This is where we are able to see the ensemble focus probabilities as they were given by ECMWF. The colors show where the members agree the most. So whether it is the low, that is where there's a low number of ensemble crossing the threshold. But where it is red, there is an agreement. And where there is agreement, that means that there is a stronger signal. So red means a stronger signal. And as you go down the color ramp to yellow, you get a lower signal. So the story map basically tells you a story in 4 steps. The first step is the signal. It shows you that ECMWF data is predicting that there's going to be rainfall beyond the threshold set for that specific time period. And then the next, once you scroll down, you go to the observation. The observation is IMAGE data observation, where it's able to tell you what actually happened during that day. So you first look at the forecast, and then you look at the observation. After the observation, you have the impact that particular event costs. That is the MDAT data that we are yet to integrate into the system for now. But once integrated, it should show the areas where there was impact, and then you can compare with the forecast to see, did the forecast predict this? And then to the decision layer, which is the green side, the greener map on your top right. This is the admin 1 risk layer. So basically here you are able to rank the three highest exceedance, the 3 highest admin 1 levels that exceeded the threshold. So here, the decision makers, whether it's the Met or whoever is mandated to actually initiate fallback mechanisms, can actually come in here and say that, see, this area, maybe, for example, we were doing a run and Kilimanjaro was very much affected. You can see some red here. You can see Oromo region in Ethiopia. It's also not green. So that means that there's some exceedance probability on that area. So you are able to know that here in Oromo, you have some trouble. And if you go back to this second map where the story starts, yes, you are able to see on pixel level, because admin 1 level shows you on a higher scale. But if you want to see where exactly in Oromo is there going to be exceedance probability, because Oromo is a huge region, you're able to see here on the pixel level. So basically what the system does, it turns the ECMWF data sets that maybe people who are not using or didn't have the means to use, it turns them into actionable decisions, because you have the data, you have the forecast, and it can pin you direct to where really is there need for action. So I think that is it in terms of the system. In terms of what we have delivered, so far we have the website, and it's basically Flutter front end and XRA T-Tiler backend, and it is an interactive platform. You've seen the calendar index and the story map, and we also have the admin 1 aggregation with the severity classification. Currently, we are working on the Ice Chunk virtual store publication to a public bucket, and we are also trying to benchmark cost, because currently the current runs I've done them on my local laptop. I've not had the opportunity to have a virtual machine, so it's quite heavy. So we are looking at maybe what is the cost of running this, maybe for like 1,000 days or for a certain number of days. So our plan is to maybe have this on the cloud so that it can run maybe on a node, and we can test the full 1,000-day exceedance archive across all the windows and the return periods. There we are able to see, for example, events in 2024. How did that event build up? What did the forecast say? Where was the opportunity missed? And probably we will now come up with a missed opportunity index and the Bayesian decision support layer, and more documentation to make the pipeline reproducible, and hand over some of the work to ECPAC. Maybe it can be useful to them in terms of getting the missed opportunities. Yeah. So I invite any questions, reflections. Thank you for listening to us.
Thank you very much, Mass team. Thank you. We are all of us very looking forward to the live demo during the final day. It will be very promising. Yes, for sure. Yeah. Any questions, please? We'll have 2 more presentations. So after that, there will be a ton of questions and answers. And anyone in the audience who want to ask something, please type on the webinar chat, and we can address it at the end. Yes, and now this is the moment for causal CEI. This is a project, leaded for Irene, Sebastian, and Anne-Marie. I think Anne-Marie is the one who is going to present. The floor is yours. When you're ready, please. You are already sharing your screen. Hand over to you.
Yes, hello.
Sorry, Sebastian, it's you.
Yeah, I'm starting and I'm handing over to Anne-Marie later. Yeah.
Perfect.
Thank you very much. So our project is called Causal Chi. So Irene is not with us here today, so Anne-Marie and me will present. And yeah, we're from GSV Austria, and we are presenting a compound event index that we also want to understand in a causal way. So to motivate the problem a little bit, we can look at a few pictures, or 2 different pictures in particular. So on the left-hand side here, we can see a dried up lake. That's the Neusiedler See in Austria. It was in the summer of 2022, where over the preceding sort of year, we had a lot of high negative precipitation anomalies, while still having... sorry, could someone...
Sorry, yes, Mark, do you mind to mute yourself? I think it's you.
Neo challenge.
Yes, please, can you mute yourself? I think Mark, it's you. Can you hear me? I'm afraid. Yes, thank you.
Okay, thank you. No worries. So background conditions, a lot of negative precipitation anomalies compared to the usual climatology, while at the same time having above average temperatures, which is sort of the driver of evaporation here, potential evaporation, which then leads to a strong negative climatic balance, and which then can lead to impacts that we can see on the left-hand side, like parts of a lake completely drying out. On the right-hand side, we have this picture in a different context, in the energy system context. We see in the top subplot the generation of some renewable power systems is the colored stacked power blocks at the bottom, and on the top the black line is the demand. So we can see that in this situation we had a clear gap between the generation of renewables and the demand, and basically it becomes a problem the larger, in simple terms, it becomes a problem the larger this gap is. So the higher the gap, the larger the stress on the energy system. And this is the core problem that we want to quantify by deriving a compound event index that describes this total stress for energy systems, or for the energy system infrastructure specifically. Okay, and our workflow is divided into 3 sections. So at first we have weather regimes. Those were mentioned in the talk 2 talks before, so I won't spend a lot of time on it. This is sort of the background situation how the weather behaves, and that sort of leads or that elevates levels for potential events that have an actual impact. The second is the index. CEI stands for Compound Event Index, and we condition this index based on the weather regimes to improve the predictive capability of this index. And finally, the third part, the explanation part, is that we are using an algorithm that is based on Granger causality to sort of use all of the different input parameters from 1 and 2 and try to causally explain what is the background, what is the elevated background in which variables, and what are the specific event triggers for events that cause a high total stress on the energy system. Yeah, so for the weather regime patterns, we are taking the weather regimes from GRAMS 2017 as sort of a easy to understand baseline. These are not part of the workflow pipeline, but we are qualitatively comparing the method that we actually use in the pipeline with the GRAMS weather regimes, and these sort of represent macro regimes or background conditions. The next slide, please. And the weather regimes or the patterns that we actually used are based on SOMs, so on self-organizing maps, which we can also see on the right-hand side, macro regimes from SOMs. So we did an ablation study already and arrived at sort of an somewhat optimal cluster separation with a 10 by 10 grid. So that means that we have 100 different SOM patterns, and we use k-means on top of that as a post-hoc clustering to bring the 100 SOM patterns down to 7 macro regimes. And those SOM-based macro regimes are what we see on the right-hand side. And those we compare qualitatively to the GRAMS regimes because those are well understood and well studied. And yeah, so the SOM patterns are then sort of the background conditions with 100 different patterns, and we link them to different compound events. And we do this by looking at what we call a lift index. It is a probability that an event at a grid cell is happening conditioned on the specific regime, divided by the probability of the event happening unconditioned. And this sort of gives us an indicator. So for example, we have a compound event that is called Dunkelflaute, that my colleague Annemarie will explain in a bit. And the lift index basically tells us that a specific regime is causing Dunkelflaute compound events 5 times more over the climatological average. So something that's sort of the link, the bridge between the patterns and between the specific compound events. And yeah, for more words on the compound events, I'm handing over to Annemarie now.
Thank you, Sebastian, for handing over. So we have just heard about some stress events affecting the energy infrastructure. These are so-called compound events. Compound events because events involving more than one variable stress the energy system most. Variables are in this way wind or solar capacity factor. When they are low and the demand is high, this stresses the energy system really badly. We have a list of 14 types of definitions of compound events resulting from international projects and diverse literature we reviewed, and 5 of them we will use in this study. These are listed on the right-hand side. And they are taken from our proposal. These 5 types are still under review, as our mentors would like to provide feedback on names, definitions, and detection rules. So there is a little bit of work to do on this topic. I only want to mention one of them more precisely, called the Dunkelflaute, as Sebastian already mentioned. Dunkelflaute is defined as an event in which low wind, low sunshine, and high demand coincide. For example, when the wind capacity factor is lower than 10% and the solar capacity factor is lower than 15% over a period of at least 24 hours, and occurs primarily in the winter months. The capacity factor mentioned essential for the definition is the ratio of the power plant's actual production, so what the plant is producing at the moment in real time over a given period to its theoretical maximum output if it ran continuously at full rated capacity. The first two types listed here will be used for the proof of concept of our study for the cause trigger analysis according to the Hlavac-Schindler definition. So here I want to show that there are different definitions for the Dunkelflaute. Some are more strict and some are not as strict as the others. So I brought three definitions. One that is really strict, you can see it in the blue bars. The green bars and the yellow bars show definitions that are not as strict as the other ones. And the gray bars show where the strict definition from Stoop hasn't any event at all. Shown are these events for different countries based on the ENSO-E data. And the key findings of this figure is that fixed thresholds fail across the European fleet. There are 20 out of 51 zones that are uncomputable under the Stoop fixed threshold rule. For our proof of concept, we need a sufficient number of events to obtain robust, meaningful statistic for the European domain. And the green bars show our definition of the Dunkelflaute. And given the higher number of the causal chi definition, we expect statistics to be more robust. Here, we use different sorts of data to validate our approach, our method. So we use the ENSO-E data, which is data that contains hourly, historical, and real-time European electricity market data for different bidding zones. For example, the demand or other parameters, and is available since 2015. The purpose of this data set in our project is the chi validation, so the validation of our index. We use the PACT 4.2 data, the Pan-European climate data set that provides daily information on climate and renewable energy. For example, the capacity factors and the demand at historical and future time periods. We already have seen what this data set is able to propose. We wanted to compare these two data sets to be sure that we are on our right way. We can see here in the graphic that the some of the lines are really good, lying above each other. And there are also some lines which are not really promising. This is because some of the data we loaded has gaps, and some of the data we loaded have are not aggregated for the whole bidding zones, so only per country. And we have to summarize. We have to aggregate all data, and this is a known and fixable issue we will do in the future. Until the end of the project. So the take-home message is that the PACT data is able to reproduce the ENSO-E demand data really good. And ENSO-E is only used for as mentioned, validating what is happening post 2015. So what are our next steps? Sebastian mentioned the weather regimes, grams and zooms. There will be a fine-tuning on life cycle and climatology. The compound event detection is on a good way. We only have to finalize the definitions we are working on with because all the computation setup is already done. For the compound event index, we also have prepared the workflow. And the two mentioned events that we want to analyze are also set up. I showed some ENSO-E validation. This is also an ongoing work, and we will finalize it until the end of the program. And then the causal chi decomposition. Also, the setup is on a good way, and we have to define the framework on a final stage and apply the change trigger algorithm on our data. And in the end, we also want to visualize our findings on a dashboard, finalize the documentation and the packaging. So thank you.
Yeah.
Yes.
Ah, sorry, I couldn't unmute myself. Sorry, thank you very much, Sebastian and Anne-Marie, for your presentation. Very, very, very well done. And now we have the last but not the least presentation from today, this first session of the midterm webinar. So we are very welcome to have with us Taranun Tafasum. This is the team member for the project Tree Hydrate. So the floor is yours. When you're ready, Taranun, you can start.
So thank you very much. There were really, really nice and wonderful presentations and a lot of really well done projects based on Code for Earth. And in my case, it's a much more simpler approach to the Challenge 22 that was uploaded. So without any further ado, because I'm aware that there is literally just 6 minutes for me to cover up everything. So I will start with what Trihydra is, and it is simply a very basic and quick-paced verification system based in 3 layers for streamflow anomaly detection. So, and why was Trihydra thought of as a good solution to the problem presented in Challenge 22 for Code for Earth? So the idea behind Trihydra was a simple pipeline that in 3 parts detects if there are anomalies in this time series of streamflow, if the machine learned outputs of an observation time series is actually hydrological plausible or does have some suspicious spikes or artifacts. So this is done mostly for automated checks for both observed and machine learned predicted daily streamflow for data which is being forecasted by ECMWF. Essentially, the data and test cases are based on the caravan observation data, based on which the AIFO deterministic forecast was conducted by ECMWF, and both of these data were provided to me. And currently, I am doing the tests on specific basins which have very specific characteristics for the time being, and every basin has a different characteristic time series for the entire stream flow, because some of them are regulated, some of them are located in a more tropical region, and really entirely different time series and very different characteristics. And so the idea was to flag if there are missing values, if there is a spike, a dip, or if the time series has entirely drifted, or if there is a step shift, if you know what I mean. The figure you see here of the time series, which has tiny little dots, here I tried to quantify some of the high flood events within the time series. So anything above the Q95 percentile would be candidates to be flagged as flood events, which would then also be propagated to the next layers to be verified. So currently the progress is that I have conducted a literature review to find out what sort of anomalies would there be normally in a time series and how to approach them based on existing literature and how to, which anomalies we would rather like to see and flag in a time series data, be it just for data quality and analysis check, or be it for hydrological signatures check of the observation and the machine learned time series. And of course, there would be data exploration for both the observed and machine learned time series. And currently I have completed up to layer 2, and it's in progress of being cleaned up through the codings and yeah. So if I talk very briefly about layer 1, so this is the part where it is entirely data-based. It does not depend on any of the hydrological characteristics of the time series or the basin itself. So it is just simply very simple structural checks if there are any missing data, if there is an inconsistency with the time steps, or if there are duplicate stamps, duplicate values, if there are very long internal gaps, if there is any negative discharge at all, because sometimes it seems that in observational data, there could be negative discharge. In machine learned outputs, there could be outputs which are generating negative discharge, which is less likely, but it can happen. And it also checks on behavioral diagnosis. If there is a flat line that's happening, if the variability of the flow is very low. And of course, I've mentioned about the spikes, the dips, the step shifts, and of course, the gradual drift. For layer 2, this is where the hydrology comes in, because the streamflow time series is not only dependent on data itself, but of course, it has a characteristics which is driven by its hydrological properties and certainly at the basis. So here, a number of parameters are calculated, because the essential idea is to form a dictionary where the indices are calculated and listed that, okay, this basin has these kinds of characteristics represented through their indices. And the idea is that this layer would allow us to compare the observation and the machine learned outputs to see if the machine learned outputs are being plausible enough or close enough with the observation outputs. And yeah, the core framework is that there would be 3 layers. First one would be for quality check diagnostics. The second one is for hydrological signatures. And the third one, which currently I'm working on, is more contextual dependent. So after layer 1 and layer 2 is done, we would then check with any available auxiliary data of the catchment, or if precipitation data is available, or any form of auxiliary data, could be land slope, could be base flow, could be anything. So the catchment attributes, and of course, with the neighboring stations, there would be a comparison made so that it can be verified that, okay, that this particular flag is probably only not a flag, but it is event driven. So that would then be diagnosed as it's an event driven output and not an anomaly. So these flags are just evidence for okay, there's something that's going on, but they're not exactly automatic verdicts. So the next steps would be, of course, starting with layer 3 and creating summary outputs. I am yet to build a ingestion pipeline for the entire dataset that would be used by ECMWF, and it consists of more than 800 stations. So another stretch goal is, if I have enough time, which I plan to do, is create a dashboard where you could just see the summary of each of the stations that, okay, this percentage of data is missing from here. The machine learned outputs in this station is closely aligned with the observational data set, and so on and so on. So with that, I end my presentation, my tiny little presentation of TriHydra, and I hope you've enjoyed. And if you have any questions, please let me know.
Thank you very much, Saranum. Thank you very much to all of you. We are very, very impressed for the progress you have done so far. It isn't true, Tina.
Absolutely. So it's
Yeah.
really amazing. And I
Yeah.
just look at what Gianpaolo wrote, you know, from within 8 weeks from the start. So congratulations to everyone. That is impressive, I have to say.
Yes, yeah.
So
So-
yeah, and I'm really looking forward to the final day. But before that, I would like to give, so we have asked for questions. Sorry, by the way, I'm talking about strong events. I'm in the center of a very strong event. The world goes down. No, so we asked about any questions to the team, So, but we haven't seen any questions, or we still have
no,
a few minutes.
I haven't spotted any, but
Yeah, so
please feel free to type or to ask whatever you.
you know, also we also can, you know, manage that you can ask your questions from the audience, because I also see a lot of colleagues.
And they're also mentors in the
Yes.
attendees in the
Yeah.
webinar. We're very grateful to be here
Yes,
supporting
thanks
your
a lot.
teams.
Good. Then I don't want to keep you unnecessarily long. As there are no questions right now, you know, please feel free to reach out to the team members, or, you know, if you want to connect with them, to Esperanza and myself, and we can help you connect with teams. And mark your calendars. We have next week another webinar, and where we have the next or the remaining 7 projects, and that's VA Toolbox, GeoBridge, Clam, GIK, IceChain, Nebula, Airwise, and Tabula Coloris. So with that, I mentioned it already. You can also mark your calendars. The final day will take place in Reading. And with this celebration picture, I would like to end the session today. Thanks a lot to all the participants, all the presenters, for your amazing work, for your presentations, for your time and effort you put into Code for Earth. The program works only with you, and of course with the mentors. And we are really, really grateful to have you with us. And there's another chat. Yeah.
It's the same feeling. Everyone has done an excellent job.
Yeah, absolutely. Thanks a lot to everyone. Have a great day, and maybe see you next week at the other session with the remaining projects. Bye-bye.
Bye-bye. See you Wednesday.
Thank you so
Bye-bye.
much.
Thank
Bye.
you very much.
Bye-bye.